Welcome back. Let's continue our first quarter review. So we're here on number 22, finding the determinant. So to find a determinant of a second order square matrix, we do the main diagonal product, 11 times 5, minus the product of the secondary diagonal, 3 times 16. So we have 11 times 5 minus 3 times 16. And that is 7. So our determinant here is 7. A third order matrix. So we start here with this 3. And we multiply that by, so that's the first row, first column. We make a little matrix down here, a little 2 by 2 outside of that column. So we're in the first column, so I'll use the bottom and then the second 2 columns and do a 2 by 2 determinant here. 2 times 3 minus 5 times 0. Okay, and then I subtract. Okay, I always subtract first. Here's a 2 by 2, I subtracted. Here's a 3 by 3, I subtract. When I add another one, then I add. Okay, so I'm subtracting, and then I move to this 5. 5 times, and then I do a second order determinant. But I don't use the middle column this time because I use that up here. I use the 4, 6, and 0, 3. So 4 times 3 minus 6 times 0. And then I add, and then I use the 7. And that's in the third column, so I use the first 2 columns. 4 times 5 minus 6 times 2. Okay, so I've got 3 times, and that's 6 minus 0, so 3 times 6. Minus 5 times, 4 times 3 is 12, minus 0, so 5 times 12. Plus 7 times, and then I have 20 minus 12, which is 8. So that's 18 minus 60 plus 56. And that is 14. Solve the system of inequalities by graphing. So I'll make an XY chart for this first one. 0 for x and a 0 for y. When I put in a 0 for x, I can divide by 3 and I get y is 3. So I have the point 0, 3. When I put in a 0 for y, 9 divided by 2, I don't like that. So I'm actually not going to use that intercept. So I will find the slope. The slope is the opposite of a, which is negative 2, over b, which is 3. So the slope is negative 2/3. So that's down 2, right 3. As many times as I can fit. And then up to left 3. Okay, and this is or equal to, less than or equal to, so I will make it a solid line. Okay, and then I'll test the origin. When I put in 0, 0, I get 0 plus 0, which is 0, is less than or equal to 9. And that is true. So this line will end up shading toward the origin. Okay, then x is less than or equal to 3. So x is 3 right here. And it's or equal to, so I will make it a solid line. And when I shade, I have 0 is less than or equal to 3. That is true, so this one will shade toward the origin. Y is greater than negative 5. So y is negative 5 down here. It is not or equal to, just greater than, so I want this to be dotted. And then when I shade it, I have 0 is greater than negative 5. That's true, so this one shades toward the origin. So far, it's this region that's shaded every time. Okay, and then I have I have one here that looks like it would be easy to put into slope-intercept form, but a y-intercept of 20 doesn't look fun to work with. So I'm going to find the x-intercept. Okay, so when x is 0, we'll divide by 1 and get 20. So I don't really like that one. But when y is 0, I divide by -5 and get -4. Okay, so at -4, 0, I can graph that. From there, let's find the slope. M equals the opposite of A, which is +5, over B, which is 1. So the slope is 5. So up 5, and right 1, and down 5, and left 1. And it is underlined, so I will make it a solid line. And when I plug in the origin, I get 0 plus 0 is less than or equal to 20. That is true. So this one shades toward the origin. So every one shades toward the origin, and it's this region that got shaded all 4 times. So we have a polygonal convex set right here, this quadrilateral, and we need to name the coordinates. So there's one here at -3, 5. There's one here at 3, 1. Here at 3, -5. And here at -5, -5. Okay, determine symmetry with respect to the origin. So is there symmetry here with respect to the origin? So to find that out, we do f of the opposite of x, and we do the opposite of f of x, and see if those are the same. If those are the same, then this will have rotational symmetry with the origin as its center. So f of the opposite of x, 3 times -x to the 11th power minus 6 times -x to the 2nd power. Okay, now this odd power does not cancel out this negative, so I get -3x to the 11th minus, and this even power does cancel out this negative, so this negative goes away, but there's still a negative here. Okay, so there it is simplified. Now I do the opposite of f of x, which is negative distributed on 3x to the 11th minus 6x squared, and that gives me -3x to the 11th plus 6x squared, and these are not the same, so no, there is no symmetry about the origin in that function. So for h of x, I do h of the opposite of x, which is -x over 5 times -x squared. Okay, now this is an odd power, a power of 1. It does not cancel out that negative. This even power does cancel out the negative. Okay, then I do the opposite of h of x, which is -x over 5x squared. I can put this negative into the numerator, the denominator, or the front. It does not matter where. This one has one in the numerator, so I'll put it there. And those do match, so yes, there is symmetry with respect to the origin. Okay, so we'll check this function to see if there is symmetry with respect to the x-axis. And if there's symmetry with respect to the x-axis, then it will reflect vertically and land right back on itself, which means for every y, the opposite of y also exists on the graph. So I'll test -y minus 7 equals x squared. Okay, now this right side already matches the original, and there's no way to change that. It's got an odd power. It's not going to cancel out that negative. So no, there's no symmetry there. How about the y-axis? If there's symmetry about the y-axis, then it can flip horizontally and land onto itself, which means that for every x, the opposite of x will exist. Y minus 7 equals the opposite of x squared. This squared is an even power, so it cancels out that negative. So yes, there is symmetry here about the y-axis. Y equals x. If there's symmetry here, it would flip over that diagonal line and land right back onto itself. So y equals x, which means x also equals y, so I can flip those. I can switch the y's and the x's. X equals, or x minus 7 equals y squared. Now I have to see if I can algebraically make that match the original. So I'll get x squared by itself, so I'll add that 7. X equals y squared plus 7. And then when I square both sides, I get x squared equals y to the 4th plus 14y squared plus 49. That does not match the original. No, there's no symmetry about y equals x. And y equals negative x, which also means x equals negative y. So I'm going to switch the x's and y's and negate them. So y becomes negative x, and x becomes negative y. Okay, so this even power cancels out that negative. So I'll do that and move that 7 over. So I get negative x equals y squared plus 7. And I can square both sides. And I'll get x squared equals, and it's going to be the same as what I have right here. And that does not match the original. So no, there's no symmetry about y equals x. Describe transformation. So we're starting with a cubed function. So that's a function that looks roughly like that. And two things happen here. Neither of them are inside of the cubed function. So they're both vertical. There's a vertical dilation. So one is a vertical dilation by 5. So all of the y values stretch 5 times. So y values get multiplied by 5. This gets much taller. And then it shifts up 7 because it's adding a 7 here. Okay, once again, there's nothing inside the original function. This is the original function right here. There's nothing inside of it. So first, it will shift vertically. It's going to shift down 2. Then the absolute value says that any negative outputs cannot be, so they have to flip to become positive outputs. So all your negative y's become positive y's. Okay, so this graph shifts down 2, so it looks about like that. But then all of these negative outputs get mirrored up here like that. And these go away because of the absolute value. Okay, then this next one we have a horizontal dilation and a horizontal translation. These are both inside of the cubed function, so they're both horizontal. So first, there's a horizontal dilation by the reciprocal, 1/11. So all of the x values get divided by 11. So it becomes way skinnier. Then it shifts left. And it shifts left by 3/11 of a unit. Okay, this one starts with absolute value. So absolute value this time is not a transformation like it was down here. It is the original function. So it looks about like that. Okay, here inside the function, we're multiplying. There is a horizontal dilation by 1/3. All of the x values get multiplied by 1/3, and then it shifts down 8. Okay, here inside the function there's a +2. So that means it shifts left 2. Then multiplying outside by a negative is a vertical reflection, so it flips over the x-axis. And last, inside the function, we have a -2, which means it shifts right 2, and then it shifts up 8. So here, identify the parent function. The parent function is the square root of x. Okay, so that is a function like this. I'll dot it in. 0 square root is 0. Square root of 1 is 1. The square root of 4 is 2. The square root of 9 is 3. So that is the parent function. Okay, but it has a horizontal reflection, which means it flips over the y-axis. So all of these reflect over here. So it's going to look like this. Okay, now here we have f of x equals x squared. So 0 squared, 1 squared, negative 1 squared, 2 squared, and 3 squared. Okay, so it will be a parabola right here, and then it's going to shift 4 units to the right. So this is our final graph. Find the inverse of each function. So we do that by switching the x and the y. F of x is y. So we have x equals 24y minus 31, and we solve for y. So we get x plus 31 equals 24y, and we divide by 24. So we get y as x plus 31 over 24. So f inverse of x equals x plus 31 over 24. Okay, so here's my y. I switch the x and the y. X equals 2 over y minus 15. In a proportion, which this is, I can switch things diagonally. So I can switch the x and the y minus 15. And then I can add 15. Okay, so that means f inverse of x equals 2 over x plus 15. Okay, now find an inverse graphically. So once again, it's just switching x's and y's. So I'm going to find all my integer points, and I will switch the x and y values. Okay, so 3, 5 becomes 5, 3. 1, 4 becomes 4, 1. Negative 1, 3 becomes 3, negative 1. Negative 2, negative 2 becomes negative 2, negative 2. And negative 3, negative 7 becomes negative 7, negative 3. Okay, and this function and its inverse are reflections of each other over y equals x. Okay, so now we'll do one with a curve. So all my integer points, and I'm going to have to find some more that I can just estimate. Okay, so I'll estimate right here and here, and then I'll estimate here. So I have 5, 7, that becomes 7, 5. 6, 4.5, 4.5, 6. Okay, then 6 and maybe a 6 1/4, 3 becomes 3, 6 1/4. Okay, then I have 6, 2 becomes 2, 6. Then 4, 0, 0, 4. 2, negative 2, negative 2, 2. 1.5, negative 4, negative 4, 1.5. And then 2, negative 7, 2. Okay, and it should be a decent reflection over y equals x. Describe the end behavior. Okay, so in order to do that, we are going to graph this. So in y equals, we have 7x squared minus x to the 5th power. Okay, so there's our graph. On the left side, as x approaches negative infinity, this is going upward. So y approaches positive infinity. On the right side, as x approaches positive infinity, y is going down, so it is approaching negative infinity. For which intervals is this function increasing and decreasing? It starts by increasing. For x's that are from negative infinity up to negative 2, so for all x's less than negative 2. Then it begins to decrease. And it does that for x values that are greater than negative 2, but less than 3. And then it begins to increase again for x's that are greater than 3. Extrema. So my extremes are here, here, and here. Anytime it's at a maximum or a minimum, I can't count these because it goes beyond these up toward infinity. So these are the only 3 points I can count. So I have a minimum here, a maximum here, and a minimum here. So what type of minimum? This is not the lowest this graph will ever get, which means it is a relative minimum at negative 5, negative 2. This is a maximum, but it's not the highest it'll ever get because it goes higher here. So this is a relative maximum at negative 2, 4. And then here, this is the lowest it ever goes, so it is an absolute minimum at 3, negative 6. Determine whether a critical point is a maximum, minimum, or point of inflection. So we need to put this in our calculator here. So back to y equals. Clear that out. X cubed minus x squared plus 3. And that is not how that should look, so I'm going to start that over. So we have x cubed minus x squared plus 3. Okay, so that's what the graph looks like right there. And we're looking at x equals 2/3, which is somewhere around here. Is that a maximum point, a minimum point, or a point of inflection? And here's how we find out. We're going to look at a table, but first we're going to set the table. So second and then table set. Okay, we want the table to start at this critical point, 2/3. And we want the change in table to be 1/10, so 0.1 for the change in table. And then we're going to look at the table, so second table. Okay, so this is the critical point, 2/3. I'm going to go up just to show a little bit more and back down to my critical point and over to the output. Okay, so at 2/3, I have an output of 2.8519. Right above that is an output of 2.8609, and right below that is another 2.8629. Okay, now this right here is the lowest in its area, which means it is a minimum. Okay, so back to y equals, and we have 3x cubed minus 18x squared plus 36x minus 23. We'll set the table, and we'll start the table at the critical point of 2. Keep the change in table at point 1, and look at the table. We'll go up and back and over. So at x is 2, we have an output of 1. Right above that is 0.997. Right below that is 1.003. Now this is between those two. Okay, it's not the highest of these three, it's not the lowest, it's between them, which makes this a point of inflection. And last, state the equation of all asymptotes for the following function. Okay, so to find the vertical asymptotes, we set the denominator equal to 0. So 5x minus 12 equals 0. Okay, now really 5x minus 12 can't equal 0 because it's a denominator. So we have 5x cannot be 12, so x cannot be 12 fifths. So there is a vertical asymptote where x is 12 fifths. Okay, then for a horizontal asymptote, the numerator and denominator have the same degree, so I can take the coefficients there and say there is a horizontal asymptote at y equals 17 fifths. Okay, here again I set the denominator equal to 0. 4x squared minus 8 equals 0. So 4x squared equals 8. And I can divide. X squared equals 2. And then take a square root, and I get x equals plus or minus the square root of 2. So that means there are 2 vertical asymptotes. There's one at x equals the square root of 2. There's one at x equals the opposite of the square root of 2. The degrees here are not the same, so I need to add to the numerator 0x squared and use those coefficients. So there is a horizontal asymptote at y equals 0 over 4, which is 0.